Morning, everyone. So we're going to continue and finish up Laplace transform. Probably we will finish the topic 4 today, and then we also jump to topic 5 because I think next week then we'll go through the tutorial. Wait, is that a good plan? Okay, maybe we see how later. Okay, let's finish this first. Yeah, so where we stopped at is the shifting properties. So actually there are two shifting properties. So just a recap, the Laplace transform is really just an integral, right? Integration. So if you just fit in the function f of t into the integral, where the function f of t is multiplied by the exponential function e to the minus st, then clearly the integral, because the limits are 0 and infinity, so after you sub in, the t will disappear, right? Because you're integrating respect to t, so after you sub in the limits, right, the t disappears. So if the t disappears, that means it only leaves us with s, the parameter s, okay? But that is actually the variable in the f of s function, which is after you integrate, you're left with the only variable s. So therefore, eventually, after the Laplace transform integral, you're going to get a function of s, okay? And then because the integral is really just trying to find the area underneath this function, the integrand function, they call that. So therefore, it is just trying to have an expression, f of s, which represents the area underneath a function. Okay? And I didn't, yesterday I didn't go through why we go through this like mindless process, it seems. Okay, the reason why we go through this process is later on you will see that because the Laplace transform is an integration. So when you integrate a derivative, later on you will see, when you integrate a derivative, the derivative disappears, right? Because fundamental theorem of calculus, when you integrate the derivative, you are actually trying to reverse the differentiation process. So what that means is, if you apply the Laplace transform to solving differential equations, as you will see later on, you notice that you don't get a differential equation anymore. You get a simpler equation to solve. Okay, of course, simpler is subjective, right? But generally, it will be simpler. Okay, so this is the purpose of learning the Laplace transform, right? Because we want to solve differential equations, and the Laplace transform is one of the, I would say, the most efficient methods to solve a differential equation. Okay, so but then of course we got to learn the fundamentals of how it works first before we can apply. So that's the Laplace transform. And talking about the shifting property, so actually there are two shifting properties. One is the shifting in the S domain. So this is called shifting in the S domain because your f of s become f of s minus a. Okay, so that means it's like you take f of s, right, and then you shift towards the right by a, because minus a ma, right? Minus a means shift right lah, if you recall your math 1. Okay, the graphical, what do you call that, shifting and then reflecting and whatnot. Okay, the graphical transformations. So therefore this minus a, you shift right. So therefore it's called shifting by the, shifting in the S domain. Okay, so and this happens when the f of t function is multiplied by an exponential function e to the at. Okay, so this is S shifting, which is pretty, I would say, straightforward. But maybe the not so straightforward one is the shifting in the t domain. So shifting in the t domain is when, right, you take the function f of t, shift it towards the right by a. Then you also activate the function only at t equals to a. Okay, so you can see the graphical representation here, right? It's like this f of t, which is represented by the green curve here, right? Originally, maybe it starts at t equals to 0 lah. Okay, originally you shift the green curve to start at the y-axis, right? But because it minus a it means the whole green curve is actually shifted to the right by a, as you can see here. Okay, and then you also activate only the green curve, right, at t equals to a. So therefore, you only look at this part. Okay? That means it's like you start the function at t equals to a. So when this happens, what happens to the Laplace transform is that, right, you just have the f of s multiplied by e to the minus as. Okay, so you can see actually there's a very interesting symmetry here, right? That is in the shifting of the s domain, right? You multiply by e to the at. When you multiply an exponential function in the t domain, then you get a shifting in the s domain. Then it's like mirror. This is the mirror. So when you multiply exponential function to the f of s, you get shifting in the t domain. So this one is like a bit of symmetry here, okay, in this property of the Laplace transform, which is actually pretty interesting. Okay, but actually we are not so interested in the graphical properties. We are more interested in how it applies. And the main part where it applies is that because in engineering systems, we get excitation functions that can be piecewise or can be defined over a specific interval. So as you can see here, if we have multiple intervals as shown here, A to B, B to C, C to D, and so on and so forth, right? And then in each interval is representing a different function. Then how are you going to handle this in the Laplace transform? Okay, so one of the elegant ways is that we can just write down the multiple functions originally given in the piecewise manner using the unit step function in one function. Okay, so it's like combining all the different functions over different intervals into one single liner. Okay, so you can see it's F1 activated at t equals to a. So this is F1. Okay, activated at t equals to a. You see, but because you turn on F1 already, so I always like to explain this, right, in the terms of turn on, turn off. Okay, because actually the unit step function is like a switch lah. Okay, so you can treat the unit step function as a switch, whereby if the unit step function is positive, then it will be a turning on. Okay, so you can see turn on F1 until at t equals to b. F1 got to turn off lah because F2 turn on already. Okay, it becomes a new function, no longer F1 already. So you got to turn off F1. So therefore, there's a negative. So when you multiply by the negative of the unit step function, actually you are turning off. Okay, so you turn off F1, but you got to turn on F2, what? Okay, then it just repeats the same process here, right, over each interval. So C to D, right, you got to turn on F3, turn off F2. So therefore, you have this part here. Okay, so notice that the unit step function, A, B, C, so therefore they are just turning on and off, right, during each interval transition. Okay, yeah, so this is the rewriting, right, of a piecewise function into a single liner, right? But of course, this is easy, right? As you can see in the next example, right? But because this is f of t, it's not f of t minus a. So therefore, there requires some manipulation here to make it into this form. Okay, this form, f of t minus a ut minus a, which is like what we did in this example. Okay, can see that the function is t squared. It's not t minus a squared, it's not t minus 2 squared. So therefore, we got to manipulate into that form. Okay, which is not difficult, just algebraic manipulation. Yep, sure. It can be any function. It doesn't need to be mx plus c. It doesn't need to be a linear expression. It can be any function, but the function only appears at a. Before a, there's nothing. Doesn't matter. Can be a negative function also. Can be any function. Okay, what's important is that you can see that before a, I got nothing leh. So nothing, you cannot like activate the function, right? Nothing to activate. So let's look at this example, and there's a sad news today, and that is I lost my cable to my writing pad. So I'm going to write directly here. Okay, not to worry, you still get the uploaded writings in my nice handwriting. So now I'll just write on the board. So which one should I write on? This one is okay? Okay. Yeah, so your cable, is it the But then you're not using You can don't use
I think it's Dongbing one.
My one is not the Type C one. Where's the old school one? No. Oh no, not that old school. The in between one. Huh? This is good, man. Yes, it's this one. Okay, let me try. Let me try. So this one, if it works, Tiamson will get extra CP. Okay, let me try. Cannot. Nope. I think maybe this one is charging one. Because got two types. One is charging, the other one is the whole tablet. Okay, let me try. I just take this. Let me try. Okay. Wait. I probably have to reopen this again. Okay, it works. So the CP goes to. Okay, thanks. We are safe. So now let's continue. So let's write down the f of t using the unit step function. Okay, and then we will do the rearranging to write it into the proper form. Okay, and then we write down the Laplace transform. Right? So therefore, this f of t, you can see that it's three functions then activated from 0 to 1, then 1 to 3, and after 3 respectively. So this expression can be more concisely written as f of t equals to, right? So you can see 2 is activated at t equals to 0. So therefore, you can safely write 2, or if you want, you can put u of t. Okay, take note that 2 and 2u of t is actually the same thing. Okay, because later on you see that, right? You write e to the 0t, e to the 0s is also giving you the same Laplace transform. You'll see what I mean in a while. Okay, so you see this one activated at 0, so it's t minus 0. So t minus 0 just t lah. Can Okay, then the second function, right? So now you plus. Then you have to turn on the second function, but you have to turn off the first function, So therefore, this becomes turn on t, then turn off 2. So you're going to put t minus 2. So then you have a u activated at 1. Okay? Turn on t, turn off 2, activated at what? At 1. Okay? Because t is activated at 1, what? So you're going to turn on t at 1. And finally, just repeat the same thing. So this one plus. You turn on e to the minus 5t, but you have to turn off t. So this is to be done at t equals to 3. Okay, and that's the end. You need not turn off e to the minus 5t because it never says that it needs to be turned off. Because it continues all the way to infinity after t equals to 3. So no need to turn off the last function. Yes? Then you got to turn off. So let's say this one, right, is like maybe go to 6. Let's say this is go to 6. Okay? Then you got to turn off. That means you got to minus e to the minus 5t at t equals to 6. So times ut minus 6. If there is this term, right? If there is this limit, right? Or is this bound? If there's this bound, right? You got to turn off that expression at the end of that bound. No lah, because he asked the question, right? So if let's say there is a bound here, that means this expression, this function only activates until t equals to 6. Then you got to turn off the function at 6, or else it's going to continue forever. Yeah, you add it. So like that, it's like together one. Is it alright? Okay, so I remove this one. Okay, so now what do you notice? You notice that, right, the t minus 2 here doesn't agree with the t minus 1 here. Then this one, e to the minus 5t, the t here, this one t minus 3. So cannot because your shifting property is actually this. Because I mentioned here, you must make the argument the same. T minus a. This one must be the same. Okay? So therefore, you got to rewrite. So you got to rewrite it into the t minus a form for all terms. So f of t, 2 constant doesn't matter. So 2, you can just leave it. This one no change. Then this t minus 2, right? You got to make it t minus 1. But t minus 2 is just t minus 1 minus 1, what? So just let it be t minus 1 minus 1. Then ut minus 1. So you can see that this one the same already. T minus 1, t minus 1. Then the same thing goes for the exponential term. So plus, actually the strategy is always the same. So you just force in the t minus something. So this one minus 3 ma. So therefore become t minus 3. But you can anyhow minus 3 what? So you plus 3 back. So let me put a bracket. Okay, then the minus t also the same. Become t minus 3 plus 3. So then times ut minus 3. So then you see the t minus 3 here, the t minus 3 here, agree with the t minus 3 here. Okay, so basically the f of t minus a must be the same as the ut minus a. But then you got to self-correct lah. Okay, so you minus already, then you plus back lor. Any objections? So if no objections, actually we can kind of do the Laplace transform already. Okay, but maybe I just rewrite it in a neater manner for you to see it more clearly. So the first term no change, plus, okay, so you see this term, this one got t minus 1 times ut minus 1, right? So actually the second term, really no need to change also. Okay, but, okay, maybe let me write it more nicely. So this is t minus 1, you let it be. Of course, you can multiply in the ut minus 1. Can multiply in, but like a lot to write. Okay, but never mind. So you just let it be. Remembering that there is a ut minus 1 outside. Okay, then this term, right, you simplify. Because you have e to the minus 5 times plus 3. So it's actually e to the minus 15. Okay, so it's actually e to the minus 15 times e to the minus 5 t minus 3. You can check the math. Okay, so minus 5 times t minus 3, then you have a minus 15. So then the same base, so therefore just take it out. Okay, then minus, so the same thing for here. This one will be t minus 3 plus 3. So this is one term by itself. Okay, wait. Change another bracket. So which means at this juncture, right, all the terms ready for Laplace transform because all in this form ready. Okay, now all in this form. Nice for Laplace transform. So now do the Laplace transform. Okay, so which means that the Laplace transform of f of t, or you can write f of s. Okay, so we do term by term. 2ut. But 2ut, then you a is 0 ma. A is 0 means e to the minus 0. E to the minus 0 is just e to the 0 is 1 what. So therefore it's just f of s. Okay, but what's f of s? F of s is just Laplace transform of 2 what. So therefore it is just 2 over s. So this is the first term after Laplace transform. Any objections? Okay, then let's look at the second term. Second term is t minus 1. T minus 1 ut minus 1. So t minus 1 ut minus 1, right? What is the f of t? F of t is t. Okay, wait. This one I better write carefully or else you're going to get confused. Hold on, let me bring the whole thing here. Okay, then I can write more. Okay, so you can see this f of t, right, is 2. F of t equals to 2. So f of s equals to 2 over s. K over s ma? Okay, which is the first term. So we do term by term. Okay, second, t minus 1. T minus 1, ut minus 1. Well and good. Okay, so what is the f of t minus 1? Is f of t minus 1 is just t minus 1. So what is the f of t? T. Just replace t minus 1 by t, right? F of t is t. Then what's the f of s? 1 over s squared. So therefore the second term is 1 over s squared, 1 over s squared times e to the minus s. Because you have a unit step here. Can But you get a 1 here. But you can do 2, confirm can do 1, correct or not? So therefore 1, I don't want to write too much. So it's really minus 1 over s times e to the minus s. So that's for your 1. This minus 1. Following? Okay, so you can see that this ut minus 1, right? actually, you can choose to write the e to the minus s outside lah. Okay, right? Because this is just for clarity. Now reality is, right, to make it more concise, you can just write e to the minus s outside. Then you have 1 minus s square, 1 over s square minus 1 over s. Okay, which I'm going to do for the third term. Okay, so this one, right, e to the minus 15 is just a constant. So this one just put down, don't have to worry about it. So e to the minus 15 is a constant. Then this one e to the minus 5t minus 3, right? So this t minus 3, this t minus 3, okay. Okay, now you see, so recognize what is the f of t minus 3. This is f of t minus 3. So what's the f of t? E to the minus 5t. So what's the f of s? 1 over s plus 5. Because this one s shifting. A equals to minus 5. 1 over s minus minus 5. So you get s plus 5. So then you put down times 1 over s plus 5. Okay? Later on outside, because you have your unit step, so just multiply by e to the minus 3s. Okay, no need to write for each and every term lah, right? Because a lot to write. So might as well just take this unit step, right? Put outside can already. Then you have a minus t minus 3. So this minus t minus 3 is just like t minus 1, what? Correct not? So I straight away right? So it's actually minus, because there's a minus here. 1 over s square again. Then you have a minus minus, so it's a minus again. Then it's a 3. 3 is like 2. So therefore, 3 over s. Yes, because there's a minus here. A minus you multiply in what? So you can see that this is already the answer. So this is the Laplace transform of that piecewise function that you saw. Any questions? Yes. Yep. I did. It's just that I multiply in. You see the e minus s here? This one is like if you multiply in the unit step to each term. That's why I say that actually you no need to multiply in, but you have to keep in mind that you are actually having a unit step outside. So then after that, you just transform the unit step by itself outside the bracket. This is just for conciseness, but initially you might not see it that way. Any other questions? Yes. Oh, okay. So if you look at the Laplace transform identity here, so you notice that this f of t minus a ut minus a, this I mentioned before that this t minus a must be the same. Okay, so if you look at this multiply to this, it is exactly like that, right? This is t minus 1 times ut minus 1. It's exactly like that, right? So then you ask the logical question, what is your f of t minus a? Then obviously your f of t minus a must be this t minus 1, where your a is 1. So therefore, if this is f of t minus 1, you want to get f of s, right? But this big f of s is the Laplace transform of f of t. So you must get the f of t first so that you can get f of s. Then you plug into the right hand side here. Because f of t minus 1 is just t minus 1. So you just replace the t minus 1. If you want f of t here, replace this by t. Then look at this, replace by t as well. So obviously f of t must be t. If f of apple equals to f of apple, then f of orange must be equals to f of orange. F of orange must be orange lah. This one f of apple, apple. Is that right? Any other questions? Good. So now we are going into the really powerful Laplace transform. That is the derivative of the Laplace transform. Okay? So interestingly, if you go and differentiate the Laplace transform function, actually what happens in the end is that you are just multiplying a t to the original function. Okay? With a negative 1. Okay, so let's see what happens here. Actually, this is very easy. So you can see that differentiating the Laplace transform, right, means you differentiate the integration, because Laplace transform is just integration. But then, because you are differentiating with respect to s, because this is big F of s, what? So obviously you can only differentiate with respect to s. Okay? So therefore, This is integral respect to t. This one is differentiate respect to s. So s got nothing to do with t, right? So therefore, you can bring this ds, dds, right, into the integral. And because f of t got no s, what? So therefore, it's a constant. So I just bring it into where there is a function with s. So then if you differentiate e to the minus st respect to s, then you have to chain rule down the minus t. You see? Okay, chain rule down the minus t. Then this minus t, of course, the minus can take out. Okay? But now you notice that, right? You are doing the integral of tft times e to the minus st. Which means what? Which means that you are actually finding the Laplace transform of tft. Because now the function is not f of t, ma. The function is tft. Okay, so therefore you are doing the Laplace transform of t times f of t. Is that right? Can Okay, so in a nutshell, right, I just bring the minus across because this is this. So I just multiply by minus 1 throughout. So it tells us that, well, if you go and take the Laplace transform of t multiplied by some function f of t, actually you are just trying to do the derivative of the Laplace transform function of f of t. Okay, just multiply by a minus. So clearly, you can do this multiple times. So what happens, right, is that if you do a d square f ds square, that means differentiate twice lah. But if you differentiate twice, that means you differentiate this expression one more time. I mean, wait, let me see. Okay, so let me write. So let's say there's a square here. You differentiate one more time. Okay, there's a square here. So you differentiate again. This one you differentiate twice. But if you differentiate twice, that means you chain rule down the minus t again, correct or not? Differentiate twice. The first one, you chain rule down minus t. Then the second differentiation, chain rule down minus t again. So you multiply by minus t again. Okay, then the minus become plus. Then the t become t square. So actually, you are just having this. Okay? So then you can see the pattern already. So which means that every time you differentiate one more time, right, you have to multiply by a minus 1. The minus 1 comes from the minus t being chain root down. Okay? And then you just increase the power by 1. Okay? So therefore, this is the general expression. So if you Laplace transform t to the power of n times f of t, really, you just differentiate n times. Very clear? This one differentiate 2 times means you times t square lah. So therefore, times t to the power of n means you differentiate n times. But every time you differentiate, there's a minus being chain root down. So therefore, it will be minus 1 to the power of n. Okay? So therefore, this is the Laplace transform for a power function multiplied to the original function f of t. So let's look at example of how we apply this. So look at this function. T squared times e to the minus t. Okay, hold on. Let me just get this thing down. So you immediately can recognize that t squared, right? If you were to use the derivative property here, n is 2. So what's the f of t? E minus t. Then what's the f of s? So you got to write down what is the f of s. Because you need the f of s here, what? Before you differentiate. So therefore, this will be 1 over s plus 1. Because it's 1 over s minus 1, shifting, s shifting. Okay, now, like that, right? So what is the h of s? So Laplace transform, So now it must be minus 1 to the power of 2. So n is 2, Then after that, right, you got to differentiate twice. So it must be d ds square or d square ds square lah. Okay? Because differentiate twice, big F of s. So it must be differentiate 1 over s plus 1. Following so far? Okay, so minus 1 square obviously is just 1. Then this one you differentiate 1 by 1. So differentiate ones first. Okay, so after differentiating ones, it will be what? It will be, because you bring down minus 1, right? So it will be minus 1 over s plus 1 square. Agree lah? Bring down the power minus 1, then the power become minus 2. Then you need to differentiate one more time. So then the power got minus 2 here. So minus 2 you bring down times minus 1, become 2. Then s plus 1 cube. Any objections? Yep. Yeah. This one. Not power, this one differentiate. Got bracket means differentiate n times. This one means differentiate n times. Huh? This n equals to 2 what? There? Because there's a, this is s plus 1 to the power of minus 1. Any other questions? Okay, so you see this result. And interestingly, you look at this expression. Isn't you can use S shifting also? Now this part, right, is using the derivative property. You use this one. But this one you can use S shifting also, what? So if you use S shifting, if using S shifting in the S domain, so what's the shifting in the S domain? Okay, get the identity down. So is this one, shifting in the S domain, So Laplace transform of f of t times times e to the at, right, is f of s minus a. Okay, so let me write down shifting in the S domain. So Laplace transform of f of t times e to the at equals to 1 over f of s minus a. So then what is the f of t function? So the f of t function must be the t square, what? So therefore this is the f of t. Then the a must be minus 1. So therefore what is the f of s? So big F of s must be 2 over s cubed. But then you want to change the s to s minus 1. So the end result is 2 over s minus 1, or rather in this case s plus 1, because it's s minus 1 cube, which turns out to be the same result as if you were to use the derivative property. And this is expected because you are trying to do the Laplace transform of the same function. So it doesn't matter which technique you use. You want to use derivative also can. You want to use S shifting also can. You want to use integration also can. Okay? So therefore this thing is the same, which is legit. Usually S shifting is faster. Okay? But not all the time you can choose this. You can have this choice, what? If I change this e to the minus t to sine or cosine t, then cannot already like this one. Then this one, this one you got e minus t so you can use S shifting Okay? But if let's say I change this to sine or cosine, right? Then it becomes you're not able to use S shifting anymore. So you got to no choice, use the derivative property. Yeah, you got to use this. Cannot use that one, yeah. So now let's look at this guy. B, or maybe I should give you some time to try. Wait. Oh, okay. So now you try and then our mark attendance. This one got 3 functions multiplied together. Okay, so this t will require you to use the derivative property. Okay, then you got to identify what is your f of t in this expression. So can be multiple Laplace transform properties used together. Okay, because t derivative property, e to the minus t s shifting property. Okay, so you got to use in conjunction. So this one you try 5 minutes. So now mark attendance. Alexander is here. Leah, Emelina, Angelico. Okay, Leah maybe later. Go Sean, Jia Sean, Brian, Chen Chang, Zhen Yi not here. Ivan, Yang Ying, Emilia, Erwin, Yanqing, Zhan Yang, Dongping, Noritetsu, Xavier here, Joey, Jordan, Kayla, Kevin, Tian Leong, Sharon, Dawson, Chen Ying, Jonathan, Kun Yong, Mac, Mikhail, Mohan, Azari, Danish, Irfan, Naya here, Bing Jie, King Hong, Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese, Ruji Ratanalai, Jumpang, Jerome, Sean, Justin, Papo, Ryan, Suhadi, Johans, Wei Yan, Yi Zhong, Tianzhen here, Trisha, Yang Hong, Shi Kang, Xingzi, Zotet, Zunping Y. Right. So let me go through. So if you look at the expression here and do a comparison, right? Then n is just 1 because t to the power of n, so n equals to 1. Then the f of t must be this guy. So this is f of t. But this f of t, right, is having two functions multiplied together. Okay, but you can always do the s shifting one because this one e minus t. So which means the f of s, the f of s must be the sine 3t function, the sine 3t Laplace transform shifted by minus 1. So it's just plus 1. But what is sine 3t? Sine 3t is giving you 3 over s square plus 3 square. Correct or not? This is sine 3t, this is for sine 3t. But you got to shift because e to the minus t. So when you shift, right, the s square become s minus 1 square. So become s plus 1. Wait, so this will become s plus 1 whole thing square. Okay, wait. Okay, so it's like that. So you see, I actually used two Laplace transforms here. Two Laplace transforms property. Okay, so f of t is e minus t sine 3t. Okay, but if you look at what we did earlier, shifting in the s domain. So this shifting in the s domain, right? This becomes your blue f of t. This blue f of t. Because a is what? A is minus 1, what? So if this gives you the blue f of t, which is just sine 3t, right? That means what is the f of s? This blue f of s is 3 over s square plus 3 square, which is 9 lah. That one is for the sine function. Do when you do the plus transform. Okay, so now what is the f of s for the pink f of s? This one different. So the pink f of s is that you have to shift. So it's 3 over s plus 1 square. S minus 1, then plus 9. 3 square is 9. Then after that, you got to do the derivative. So now derivative is big G of s must be minus 1 to the power of 1 because n equals to 1. Then you differentiate f of s, which is f prime s. So differentiate this. So you just get a minus, then this one you differentiate, right? You can see that you have to bring down a minus 1. So become minus 3 over the same denominator. Then you got to use chain rule. So chain rule means, right, you have to differentiate. So you get 2 times s plus 1. You got to differentiate the denominator because you got chain rule. Hence, you will get the answer here. Because it's 2 times minus 3. So it gives you 6. 6 times s plus 1 divided by this denominator. Oops, I forgot to minus 1 at the power. Okay, so the power bring down minus 1, right? Then become minus 2. So this thing got to square. I forgot to minus 1 to the power. Any questions? So in part B, right, the derivative property is used together with the shifting property. Yes? This one. Can lah. Of course, minus become plus what? Then plus 3 times 2 is 6 what? Any other questions? Okay, good. So no questions. Means we have gone through the list of Laplace transforms here already. Okay, so this is the main definition of the Laplace transform, just an integration. Okay, finding some area. Then this is all that we have gone through. Okay, all the various properties. So we are going to take a break now, right? And this guy is Laplace, Pierre-Simon Laplace. Okay, so he's actually the advisor to Napoleon in France many years ago. Okay, so he's a smart guy lah, right? That's why we are all suffering now. So y'all take break and then come back. We're gonna do topic 5. Continue with topic 5, right? So that you have some time till next week to try out the tutorial 4 questions. So let's have a break till 10:15. Okay. let's start topic 5. Okay, so we are going to apply Laplace transform to solve the differential equations. But before we apply Laplace transform, I would like to go through Duhamel's principle first. So Duhamel's principle is another very powerful method to solve ODEs. In fact, PDEs as well. Okay, so these two methods, right? They are the like most pivotal, I would say, methods for solving differential equations. Okay, so we'll go through both. We'll go through Duhamel's first. Then after that, Laplace transform, because Laplace transform actually got something that is related to Duhamel's. Okay, but let's look at the concept of what we call an excitation to a system, to any system. Okay, so we recall topic 3 a little bit. So in topic 3, we derived the model, the mathematical model of a cooling plate. Okay, and you have gone through your midterms already, right? So therefore, you saw the cooling or heating process applied to any object, in fact. Doesn't need to be plate lah, can be human, can be air conditioning system, can be air in a gym or whatever. Okay, so doesn't matter what is the object of interest, can be cooling, can be heating. Okay, so that's the mathematical model, right? Derived from conservation of heat energy. So therefore, conservation laws are very commonly applied to derive models. So let's look at another example that you'll be extensively tested on. That is Newton's second law. So Newton's second law, another name for Newton's second law is actually the conservation of momentum. Okay, so Newton's second law and conservation of momentum, they are intricately related. Okay, so if you apply the conservation of momentum in the momentum form, as in the momentum form means you have mv terms. Okay, mass times velocity, that's momentum, right? But if you differentiate the momentum, you will get ma, right? Because mv, so m usually don't change, right? So if you differentiate mv, you get ma. So therefore, you get the Newton's second law. Okay, so in fact, Newton's second law is just another way to write conservation of momentum. Okay, or in other words, right, Newton's second law is the rate of change form of the momentum conservation. Okay, well, so let's look at a specific example. This one, simple example. So let's say you have an object that is falling in the air. Now, because it falls in air, right, or any kind of so-called viscous fluid, there is this drag force being imposed on the moving object. Okay, so this drag force, we are going to model the drag force as dependent on velocity, and this is assumed to be constant times velocity, meaning to say the drag force is proportional to velocity. Okay, so this is an assumption which is fair enough under certain conditions. Okay, so if you think about it, right, is it logical that the drag force that you experience is dependent on velocity? That means proportional to the velocity. Okay, the answer is actually yes for some cases. Okay, why? Because if you go to swim in the swimming pool, for example, when you move your hand, right, if you move super slow into when you move your hand super slow in the water, you actually don't feel much resistance. But if you try to move very fast in the water, you feel a lot of resistance. Agree? Okay. So therefore, the drag force that you feel or being imposed on your hand, right? In this case, your hand is the moving object, is actually proportional to velocity. Okay. So of course, I say this with a little bit of caveat, because it can be proportional to v square or v cube or v power 4 and so on and so forth. Okay, so there is indeed a power law for the drag force. Okay, but for simplicity, let's assume that it is proportional to velocity at this stage in time. Okay, so now if you look at the free body diagram, oh, by the way, bad news. You will be extensively tested on deriving the Newton's second law from a free body diagram in your finals. So become like physics class. That means you'll be extensively tested on deriving the Newton's second law from a free body diagram. So I give you the physical problem. You have to draw the FBD, free body diagram, and from the FBD, you are expected to derive the Newton's second law. Okay, so as usual, if you cannot derive, then you lose the marks for the part A, typically. Okay, can so physics. Now, let's look at the free body diagram of this falling object. Obviously, it has weight, mg. Okay, so let's say the falling object is moving downwards. You can see the velocity is downwards positive. Then obviously the drag force must be opposing the motion of the object. So drag force must be pointing upwards. Okay, and are there any other forces? No more, right? So therefore, applying Newton's second law, sum of forces equals to mass times acceleration. So you can see the left-hand side sum of forces, right? mg is downwards. That is in the positive direction, assume as the velocity. You can assume upwards, no problem. You still get the same answer. I mean, you still get the same equation. So therefore, mg positive minus cv, because opposing direction upwards, equals to mv prime. A is v prime. Is that right? So now, rearrange. You see v prime and you see v. So what happens? Group the v prime and v together. Okay, divide by m throughout. So you get c over m and g on the right hand side. So isn't this a linear first order ODE? Linear, right? Because you got v prime stand alone, v stand alone. Okay, is it separable? Yes, it is separable. Right? Because c and m are constants, g is also constant. So therefore, it is also separable ODE. Okay, but it is also linear. Right? Because the coefficients are constants in this case. Okay, so now we of course know how to solve this lah. Can use integrating factor, can also use separation of variables. Okay, but let's analyze this thing. Okay, before we analyze that falling object ODE again, let's look at another example. So let's say rocket propulsion. Okay, so this one recently there's a SpaceX what do you call that, IPO. Anybody bought the stock? Good. Okay, so anyway, so let's say this rocket, right, propelling upwards, propelling upwards. So therefore, let's assume the velocity to be positive upwards. Makes a lot of sense there. Okay, so what are the forces acting on this free body diagram? mg downwards, cv downwards as well. Okay, because rocket is upwards moving. Propulsion force must be upwards, obviously. So now, sum of forces equals to ma, and you see that you get p of t minus mg minus cv equals to mv prime. Okay, a is just v prime. Now, if you rearrange this ODE, you get what? V prime plus c over mv equals to p of t over m minus g. So it's a linear first order ODE again, but in this case, not separable because you have p of t here, so you cannot separate already. Okay, but you can still use integrating factor. Okay, so of course we can solve lah, no problem, we can solve, and you will be tested to solve later on. Okay, but what's important is that we got to analyze the ODE. Now, if you look at both ODEs, one is for the falling object, the other one is for the rocket propelling upwards. Okay, now we understand intuitively, right, that the motion of each object, be it the falling object or the rocket, must be caused by forces acting on them. Makes sense, what? Because if there are no forces acting on the object, then why should the object change the state of motion? So that's as good as saying Newton's third law. Okay, so in order to effectuate a motion or change of motion, more specifically, on an object, right, you need to have some forces. The force is the cause of the motion. So for example, the falling object, right, is caused by gravity. Okay, the object falls because of gravity. And the rocket propels because it has a propulsion force opposing the gravity. Okay, propulsion force opposing the gravity that is on the object. So in differential equations, these terms on the right hand side, they are called excitations. Okay, these are called excitations simply because they excite the system, they excite the object in this case. Okay, so if right hand side got something, right, that means a function or constant that is stand alone. When I say stand alone means, right, it is not multiplied to v prime, it is not multiplied to v. So this is a stand alone expression on the right hand side. Then these are external excitations to the system. Okay, this one important, right? These are external excitations to the system. Okay, so therefore, a linear ODE, right, that contains an excitation term, let's say Q of t here. Okay, I mean generally lah. So you can see my ODE here, right? Y prime plus P of t, y equals to Q of t. So this is your linear ODE, first order. So if you have any excitation term Q of t or even a constant K, right, this is called an inhomogeneous ODE. Okay, so this one is inhomogeneous if you have a stand-alone excitation term. Okay, so in other words, right, if there is no stand-alone excitation term, so much so that this is a 0, then it's called a homogeneous ODE. Okay, so inhomogeneous means not 0. So now we ask the logical question. If you have excitations that can cause a system to have a response, what about a system without excitations? Can it still have some response or not? Have some like motion solution? Okay, so now let's consider the moving object again, the falling object, but this time without gravity. Then of course you ask the logical question, without gravity can fall meh? So maybe let's consider ball rolling on the table. So that means you like roll the ball on the table, or you play billiard, okay, or you play pool lah, right? You have your cue stick, right, hitting the ball. So then the ball rolls on the table. So let's say the table, because the rolling friction is quite small. Okay, so let's assume that to be negligible, the rolling resistance. So which means to say you only experience the drag force. Okay, that means the drag force is like due to air resistance, for example. So what will be the forces in the sum of forces? You can see that because there's no gravity, because it's horizontal, the table is horizontal. So therefore, there's only drag force, so that you get minus CV, that is in your sum of forces, only one force, equals to MA, which is MV prime. So then you still get the same expression on the left-hand side, V prime plus C over MV. But in this case, you don't have the right-hand side already. Okay? So therefore, if there is a 0 here, right, this is called homogeneous. Okay? So the terminologies here, right, eventually you will get used to that. Okay? But it's called homogeneous. So if you don't have a 0 on the right-hand side after you put it in proper form, then it's called inhomogeneous. Okay, so there are two types, inhomogeneous and homogeneous linear ODEs. Okay, now, how to solve this? This one obviously can solve, just separation of variables can already. After you do separation of variables, you apply the initial condition. So initial condition is what? At time t equals to 0, let's say have some initial velocity v0. Now, you can find a particular solution to be this. Okay, we need not solve again. This one quite standard solution method. So you're going to get V0 times e to the minus c over mt. Okay, and if you look at the graph here, right, the velocity makes total sense because the velocity, right, is just decreasing. So if you try to draw v of t, so v of t has a v0 initial velocity, then times e to the minus c over mt, right, which means that the velocity is just decreasing. So v of t is just decreasing from v0. And this makes total sense, right? Because there is a drag force, So of course, the drag force is going to slow down the motion. Okay, the object slows down to a rest due to the drag force. So what's important here is that, right, you must understand two things. Even without an excitation, there is still a change in motion of the object as defined by the velocity function. That is the solution. Okay, so therefore, the system can still give you a non-zero response because there is a non-zero function here, right? If it is given some initial condition. So no excitation also can give you response if you have a initial condition. Okay, so now important understanding. There are two things that can give a system a response. One, initial condition. Two, external excitation. Okay, so keep this in mind. This one very important, right? So maybe just to make it even more physical to you, Javier, can you stand up? Come forward, come forward. Don't worry, this one got CP marks. Okay, so you see, if I give him excitation, meaning to say I push him, then he got response, right? So excitation give him response. Okay, if I want to plot his displacement function or velocity function, I can certainly plot it. Okay, come back again. Okay, so now, let's say there is no force acting on him, but I give him initial condition. Initial condition means I give him initial push. So I give initial push. Wow, he's very strong. Okay, so you can see that he also has some response even after I push. So initially I push him, impart initial velocity, right? So he has some motion. Okay, even though I do not continue to exert the force on him. It's a so-called the motion after the initial condition. Okay, understand that? So there are two things. One is continuous force excitation being applied on him. The other one is an initial condition being applied on him. Okay, so both can cause, thanks, Javier. So both can cause a response to the system. Okay, and this applies not just for like a Newton's law thing, right? It applies for other systems as well, like electrical or other forms of system, electromagnetic systems as well. Okay, so now, okay, talk about the homogeneous and non-homogeneous. So just now I mentioned that if you don't have a excitation term, right, then it's considered homogeneous. So homogeneous, right hand side equals to 0. Okay, so now we just analyze each of the ODE here and state whether they are homogeneous or non-homogeneous. Okay, homogeneous or inhomogeneous. So what's the first one? You see, I prime equals to Ri. So if you write it in proper form, in this form, so you're going to get I prime equals to, I prime minus Ri equals to 0. So homogeneous. Okay, then the second one, x prime minus 2x equals to minus 2t. So you can see the right hand side, the standalone function of t, right? Non-homogeneous or inhomogeneous. So this one got excitation term. Okay, then what about this one? So y prime minus y over t equals to 1. So inhomogeneous also. Even with a constant, is inhomogeneous. Last one. So you see this one, t prime, but there's another t prime here. So which means that if you multiply out and you factorize the t prime, you're going to get 2 minus x times t prime, then plus x t equals to 0. Okay? Or in other words, you can write it as t prime plus x over 2 minus x times t equals to 0. But the right hand side is still 0. So this must be homogeneous after you write it in proper form. Okay? So in fact, it is very easy to recognize even if you don't multiply out. As long as you have a stand-alone function of the independent variable or even a constant, right? You are going to get inhomogeneity. So like the minus 2t, right? Stand-alone function of the independent variable. The independent variable is t ma. Then like a constant, right, will refer to an inhomogeneous ODE. Yeah, correct. Okay, that term is the excitation. Okay, so let's look at the linear ODE in this form. Okay, so linear ODE y prime plus some constant a times y equals to f of t. Okay, so given an initial condition at t naught, you get y naught. Okay, so that's the initial condition. Now, what is the integrating factor method used to solve this? Now, integrating factor method, right? You just get your integrating factor. So the integrating factor is what? E to the at, right? Because integration of a dt ma. This is your integrating factor, what? But it's just e to the at because a is a constant. Okay? So then the integrating factor method, right, is 1 over the integrating factor. So therefore, the solution becomes y of t, right, equals to 1 over mu t times integral of mu of t times q of t. So in this case, times f of t dt. Okay, because you must multiply to the right-hand side function. So by the way, the e to the at is your integrating factor, which we have written as mu of t previously. So this is the integrating factor solution. Okay, mu of t is your integrating factor. Okay, so this one from topic 2. Topic 3. So what is the general solution then? General solution is 1 over mu, but 1 over mu is just e to the minus at ma. Correct? Then integrate mu of t, which is e to the at times f of t. Okay, so nothing much. This is my integrating factor solution. So now let's look at some manipulation. Now, if you let r of t be this integrand, r of t be the integrand, so then this becomes integral of small r of t. But let's assume that integrate small r will give you big R of t, because it's an indefinite integral. So eventually you still get a function of t out. So integrate small r, get big R. No problem with that. Okay. Now obviously this one, because it's indefinite integral, you got to do a plus c. Okay. So then I want to apply, because this is my general solution. Then to find c, right, I just apply the initial condition. But the initial condition is at t equals to t naught, y equals to y naught. Okay. So therefore you observe that, right, I just sub in y naught and t naught into the general solution, and I can find my c. So c is just what? C is just e to the at naught times y naught minus r at t naught. So this one nothing much, because you want to isolate c ma. So what you do, right, is you divide throughout by this. So you get e to the at naught times y naught. Okay, then you minus the rt naught, bring across. So then you sub in the c back into the general solution to get the particular solution. So after you find your c, so just sub into the general solution and you will get the particular solution. Okay, so after you get the particular solution in this form, so we just try to make it a little bit neater. So you see this e to the minus at multiply to e to the at naught y naught. You see this first term. Okay, then after you have r of t minus r of t naught multiplied to e to the minus at, the second term. Okay, now same base. So therefore, combine the power. Okay, now this part, r of t minus r of t naught, right, is also written as the integral of small r of t dt by right. But because this t and t naught will be in the limits, so therefore we change that to tau. Okay, that means this integration variable, don't use t lah. I mean, you can use t, but wait, you mess up with this limit t. So therefore, let's change it to tau. Okay, so therefore, it is really e to the minus at outside. Then integrate small r of tau d tau. Then you have your t as the upper limit, t naught as the lower limit. Okay, so, and you notice that this is e to the minus at, right? Okay, So now let's discuss what is this R of tau actually. So this R of tau. But R of tau previously, you already defined it. So it's really R of t equals to e to the at times f of t. But if this is tau, right, then all the t's must change to tau. So become e to the a times tau times f of tau. So it's here. Because previously you already defined what is your R of t. So R of t is that expression. So you just change the expression having t to having tau. You see? All the t change to tau can already. Can Okay, so now to write it the most concisely possible, this exponential term, right, can multiply in because same base. Okay? And then you have your e to the minus a times t minus tau. You see? Okay, so just combine the base, so no need to write two exponential terms. But just keep in mind that you are integrating with respect to tau, not t. Okay, so the t is just like a constant in this integral. Is that right? So therefore, this expression is called the Duhamel's principle for the ODE that you saw. Okay, so this is called the Duhamel's principle. And actually the Duhamel's principle got very powerful meanings. So let's look at this particular solution that we just derived, which is called the Duhamel's principle. Okay, so first of all, right, you notice that the first term on this right-hand side, this very first term, is actually the solution to the homogeneous initial value problem. That means, right, just now, when we solve, we are solving with this f of t on the right-hand side. That means we are solving the inhomogeneous problem. Okay? But if we remove that f of t, right, such that you get a 0 here, then it becomes homogeneous, correct or not? So when you solve this homogeneous initial value problem, right, you are going to get this term. Okay? Because you can check. So if you solve this by separation of variables, it's not so easy to solve. Okay, separation of variables, apply initial condition, and so on and so forth. Then you get this thing. Okay, so therefore the first term here on the on the right hand side is called the homogeneous solution. Okay, homogeneous solution because you are solving a homogeneous problem. Following? Okay, so now let's look at the second term here. Now this second term is actually when you solve the non-homogeneous problem. Okay, but this one we apply a very interesting thinking. Okay, now you see the integrand on the second term is this Okay, wait, look at this. What's the integrand? The integrand is e to the minus at minus tau times f of tau. Okay, now if you compare this integrand with this, you notice that they have the same form. That means this exponential minus at minus t naught times y naught, right, is of the same form as e to the minus at minus tau times f of tau. Notice that they look very similar. Okay, just that the t naught changed to tau, y naught changed to f of tau, right? Okay, similar form. So now, what happens when I change t naught to tau, y naught to f of tau d tau? Okay, compare and contrast. This one I have to compare and contrast. Now, previously, the homogeneous solution or the homogeneous problem is this. This one I have to put side by side, then you can see. Okay, let's put side by side. Okay, let's put it here. So now you notice that t naught changed to tau, y naught changed to f tau d tau. Can, right? So now, if I change the initial condition to this, but I'm solving the same ODE, then now my question is, do I need to resolve again or not? No need, right? No need. Because when I solve this, what's the solution? So the homogeneous solution, let's put it in blue because homogeneous, is y of t equals to e to the minus a t minus t naught times y naught ma. Okay? So now after you change the t naught to tau, t naught change to tau, so what is the homogeneous solution for this initial condition? So it must be y of t solution equals to e to the minus a t minus tau, because t not changed to tau already, what? So t minus tau. Then the y naught change to f tau d tau, so must be times f tau d tau. Okay, t naught change to tau, y naught change to f tau d tau. Can Okay, so this thing, right, mirrors this thing. I just change terms only accordingly. Okay, and I return the solution here. Is that right? Okay, so what is the takeaway? What is the takeaway? That means, right, that means I can actually treat this excitation f of t, because originally you have your f of t as the right hand side excitation. F of t, inhomogeneous excitation, this is what we discussed before. Okay, so this excitation, if you treat it as an initial condition, you see, f tau d tau, right? Treat it as an initial condition. Then the initial condition is activated at time equals to tau. Okay, so now this is your entire f of t. Now at t equals to tau, you take the f tau d tau times d tau. So this f tau, right, times d tau. F tau times d tau. That means it's like you are imparting a force times a short time. So what is it? Momentum. That means you give a momentum, or what we call impulse, right, to the system at time t equals to tau. Then the solution of the system in response to this impulse is this. Okay, I repeat again. If you treat the excitation as an initial condition, look at this. This is an initial condition. So the excitation over a short period of time, treat it as an initial condition, activated at time t equals to tau. So it's like this rectangle area here. Okay, you are going to get the solution of the system, the response of the system, given by this expression. Okay, now, is the f of t just this one impulse? No, right? The f of t is comprised of many, many impulses. Okay, because you can treat it as this times this, then this times this, this times this. So it's treated as a continuous series of impulses. So therefore, what is the total solution? This one is only one impulse, what? So if you have many impulses, right, what is the total solution? You must sum up all these, right? You must sum up the response to all impulses. So therefore, it's an integration. Okay, so at this juncture, because of course you are getting sleepy, so I need Xavier again. Okay, come. Okay, so just now, right, I apply f of t, right, external excitation. So I apply as a continuous force, right? So he has some response. Okay, come back. So now if I treat the continuous force as a series of initial condition, series of impulses applied to him, right? So that means the continuous force, I can treat it as pom, 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 pom. You understand? So the continuous f of t, right, I can re-represent that using initial conditions. But it's a series, continuous series of initial conditions.
Bro, so all the pom, right?
Ah.
One is all the rectangles.
Correct. In essence, right, each rectangle is negligible width. So it's like a series of punches. Okay, and it's like an infinite punches, like to mirror the continuous force, to mirror the continuous excitation. Okay, thank you, Xavier. Right. So therefore, that is the Duhamel's principle. Okay, by treating the external excitation as a series of initial conditions, I can actually get the total solution. I'm going to stop here. Okay, so this is the most important takeaway today. Right? Why I say most important? Because this Duhamel's principle, you are going to find it very difficult. I guarantee you, this is the most difficult concept in the entirety of Math 2 and Math 3. Math 3, come back to this guy again, because this guy is going to solve your PDEs as well, partial differential equations. Okay, so if you master this Duhamel's principle, you score well for Math 2, you also score well for Math 3. Okay, that's why I spend a lot of time, right, along with my assistant here, Javier, to make sure you have the idea. Okay? Yeah, so not to worry, we're going to come back and visit this again in the second order ODEs. Very powerful method. Yes. Math 3, wait, I also forgot. 7. Yeah, 7 topics also for Math 3. Okay, so I'll see you next Monday. Please try out your tutorial 4.
What is the point of the e to the power negative?